What's up, AP Calculus students? Hey, I just finished the first video, so let's do a homework guide. This is for 6.2.1. We're going to be skipping a couple problems along the way, but let's jump right into what we just finished up in the last video. Let's look at the derivative with dy dx implicit differentiation. Here we have three functions where the derivative with respect to dy dx. Hang on, let me pull this up really quick. Sorry. Got distracted by the internet. Okay, cool. What we're going to do here is we're going to take the implicit derivative, and we are then going to figure out what dy dx is. Question A does not require an implicit derivative because look at this explicit function. It is y equals x to the third times the sine of cosine of x. This is explicit, if there ever was an explicit function. So we're going to be able to, for that one, just take the derivative normally. So I'm going to write it off to the side here, x to the third, y equals, x to the third sine of cosine of x. And let's think about this for a minute. This is going to be a product rule. It's going to be x to the third is the first thing. Whoops, go back. Undo that. I want a highlighter, man. Oh, shoot. I got to write it again? You guys are killing me here. Oh, there it is. So, x to the third is going to be our first thing. Sine of x cosine. Sine of cosine x is going to be the second thing. So, for our dy dx, we need the original first, x to the third, times the derivative of the second, which is going to require the chain rule, sine of cosine of x. The outside function is the sine, so it's going to become the cosine of the cosine of x. That's a weird thing to write down. Times the derivative of the inside part, which is the negative sine of x. And we'll deal with that when we clean it up in the last step there. Actually, it's going to look exactly like that, just a negative in front. For the second part, though, plus the derivative of the first part, 3x squared, times the original second, sine of the cosine of x. There you go. Honestly, there's not much more we want to do with this. You could, if you wanted to, you could move that negative sign right there. You could move that to the front, but I'm over this problem. Let's move on. The next question that we're looking at here, I got them on another monitor here to make it easier for this. This is going to be 3xy minus x squared equals 2. This is an implicit function because we do not have a x equals or a y equals to deal with. So we're going to have to use implicit differentiation for this one. The first part is going to require the product rule, 3x and y. You can debate whether it's easier to leave the 3 alone. I actually like to group it in with the first part. So the first part is 3x, and the derivative of the second part is dy dx. Plus the derivative of the first part, which in this case is 3, times the original second part, which we're going to leave as y. And there you go. Remember, the original first times derivative of second plus original derivative of first times original second, something like that. The next part is easy. You just need minus 2x because we're taking the derivative with respect to x equals 0 because the derivative of 2 is just 0. From here, we're just going to solve it for dy dx. Let's start by subtracting 3y and adding 2x to both sides. Over here, we'll get 3x times dy dx equals 2x minus 3y. And then finally, we'll divide by 3x on both sides, and that will get us to the end of the problem. Dy dx is going to equal 2x minus 3y over 3x. Just like that. The last question, question C, is a really weird one. It's 1 over y equals x, but this is actually a really easy problem to solve because we can just do a little bit of editing to this problem right away. We're looking for dy dx. Let's just multiply by y on both sides. And that will give us 1 equals xy. Now you could do implicit differentiation with this thing, but it might be better right now to just divide by x on both sides. Now you have y equals 1 over x, better known as x to the negative first power. And your derivative now, dy dx, is just going to be negative 1 over x squared. Another common power rule derivative that we've dealt with a bunch of times there. Pretty cool. I got them all right, too, according to the answers, so I feel pretty good about this so far. Okay, let's move on to the next chunky question. I do not have a calculator with me either, which might make 661 kind of tough. Examine the integrals below, consider the multiple tools available for evaluating integrals, and use the best strategy for each part. So, this first one here, we have the integral from pi over 6 to pi over 4 of the cosecant squared of x. So already I'm thinking antiderivatives here. I know that the antiderivative of, I know that the derivative of the cotangent is cosecant squared, negative cosecant squared. So I think this is going to be the negative cotangent of x. That's it. And we need to evaluate that from pi over 4 to pi over 6. That's going to require its own problem, though, off to the side. I feel pretty good about that answer, but actually it's not too tough to do at all. Let's pull that off to the side here for a minute. Let's think about this. This is the negative cotangent of x. Again, evaluated from pi over 4 to pi over 6. Or is it the other way around? Pi over 4 to pi over 6? Yeah, I got it right. Okay, good. The cotangent of the pi over 4. Well, that's an easy one because the cotangent of pi over 4, if you think about your unit circle, or at least the first quadrant of it, pi over 6 is right there, and its coordinates are root 3 over 2, comma 1/2. And pi over 4 is this green one right there, and its coordinates are root 2 over 2, root 2 over 2. So the cotangent, which is the inverse of the cosine, is going to be the x over the y. I'm just going to kind of write that off to the side just in case you haven't done a cotangent in a while. It's the x over the y in this case. So the first one we have is the negative cotangent of pi over 4. Then we got to do minus, or I guess plus, the cotangent of pi over 6. So we're going to figure out that for a minute. So cotangent of pi over 4 is really easy. That's just 1. So it's negative 1. Next one's not so fun, but x over y is the square root of 3 over 2 divided by 1/2. I like to think about the 1/2s canceling out, which leaves us with negative 1 plus the square root of 3 over 1, which is square root of 3 minus 1. Or negative 1 plus the square root of 3. Depends on how you want to write it, like that. Okay, question B. Here is a less fun one. We have an indefinite integral, which means we're just looking for the antiderivative. So we got to think about this. We talked today in class about the integral of 5 to the y power. So we need 5 to the y over the natural log of y. And don't get trapped here. This is the derivative with respect to y, or integral with respect to y. So we don't need to do any ridiculous implicit differentiation. As far as the rest of this goes, man, I'm thinking it might be better. Let's see. Oh, you know what? Look at this. It's got a 3 in front, and it's been raised to the second power. And there's a times 2 there, too, which is the derivative of 2y minus 1. I think what we're meant to see here is that this is just 2y minus 1 to the third power. They've actually worked it all the way out for us. Because if we took the derivative, the 3 would come down and multiply in front, which is what we have. The 2 would drop down a power, and you'd also have to multiply by 2, which is out there. I think they laid it out that way for us to see it. There you go. I like that. Plus c. Kind of cool. Okay. Integral from 0 to 4 of tangent. The antiderivative of tangent. Man, I don't really know if we have a way of evaluating this. This is going to use this would be a calculator problem. I'm looking at what the book says. They say it's a calculator problem too. So this would be a calculator. I don't have a calculator, but I do have the answer in front of me. It's about hang on, I gotta find it again. I lost my spot. It's about 0.347. Again, we do not have a way of it looks like a pretty simple thing. We do not have a way of taking by the antiderivative of tangent. Tangent squared plus 1. This is a thing. Tangent squared of y plus 1. This is a trig identity. It is. It's something. Hang on. It's one of these. Let's start. Let me think about this. The only one you should ever memorize is this one. Sine squared to cosine squared equals 1. But I do know that if I divide everything in this problem by the cosine squared of x, you get tangent squared of x plus 1 equals the secant squared of x. Look at that. Very clever. So tangent squared of, I guess it's y, who cares? Tangent squared of y plus 1, you can rewrite this right away as the integral of secant squared of y dy, which is just known as the tangent of y plus c. It's kind of cool. You know what? Kind of cheap. You know, I like these problems because they're cool, but I don't know. I don't know, man. Okay, we're not going to worry about 62 right now. Second derivatives of implicit functions. It's a thing we will talk about, but it's not going to be today. 663. First and second derivatives for the function below, and use them to test for extrema over the given interval, and we're going to check the endpoints. This is going to be a fun one. Here we go, 663. It's a pretty straightforward problem. The function is y equals 2 sine x plus 3 cosine x. And the interval is 0 to pi. Okay. Let's talk about first derivatives first. Pretty simple first derivative in this one, honestly. It's going to be 2 times the cosine of x plus, or I guess minus 3 sine of x. And we will have to deal with when that equals 0 in just a moment. But because it's pretty easy to do, let's get our second derivative over here too. It's actually going to look very similar. It's going to be minus 2 sine of x minus 3 cosine of x. Not too bad. Not too bad. You know what I don't like about this is I'm looking at the answer and it's a nasty decimal, but we'll at least get as far as we can before pulling the plug on this. So what we need to do first is we need to figure out what the where this is equals 0. Yeah. So when does y prime equal 0? That's the question we got to solve. When does 0 equal 2 cosine x minus 3 sine x? That can be tough to do. What we could do, let's add the 3 over. Let's add 3 sine of x over. Equals 2 cosine of x. And I like doing that because if I divide by cosine of x now, I can consolidate the sine and the cosine into one trig function, which is the tangent of x. Like that. And that's nice because the tangent of x now has to equal 2/3. And that's actually a thing that you can do. It's an inverse tangent. It's exactly what we're going to do. So x is going to equal the inverse tangent, or arctangent, of 2/3. And this will tell us there. Now I'm going to use my phone calculator, which is not an ideal solution, but I believe it does have, if I tap this little button there, does it have inverse tangents? Oh man, it doesn't. Boo, inverse. Oh, it does. Wow. Guys, check it out. It's got inverse tangents on it. Amazing. Inverse tangent of 2/3. It's even in radians mode. What will they think of next? Thank you very much, Jeff Bezos. Oh, it's about 0.588. Cool. I like that. That's the only spot I can find where the derivative is 0. Now, as far as whether that's a minimum or a maximum, I guess what I want to do is I want to evaluate my y double prime when x is 0.588. Because the second derivative will tell us what the concavity is, and that'll tell us if that one point is a minimum or a maximum. Because if the thing is concave up or concave down, it'll at least tell us that. It won't tell if it's the most, but again, I'm going straight to the calculator. -2, where'd my trig functions go? I got to rotate. Sine of 0.588, close parentheses, minus 3 cosine of 0.588, close parentheses. And I'm getting about negative, well, it's a negative number. It's -3.6. So it's negative, and so therefore it's concave down, which means that this, all the way back over here, that is going to be a relative, concave down means it's going to be a maximum. Because a concave down graph looks like this and has a maximum at the top. Cool. Now that doesn't tell us it's the most extreme maximum because we do need to check the endpoints also. So let's make a little table and let's check. 0, 0.588, and pi. Like that. X and then y here. Plugging in 0 is really easy since the sine of 0 is 0 and the cosine of 0 is 1. This is just 3. And pi is also pretty easy because sine of pi is 0 and cosine of pi is -1. So this is -3. Down below. And let's see, as far as a maximum goes, I guess that means that this has to be the maximum. I'm going to have to use the calculator for this one more time. Sorry guys, I know this is a fun video to watch. 2 sine of 0.588, close parentheses, plus 3 cosine 0.588, close parentheses, equals 3.6. Look at that, it's bigger. We already kind of knew that, didn't we? Shoot, I could have done that. Oh, man, I saved my work. Looks like this is the maximum, and this is the minimum. Look at that. We did it. Hey, we did everything we had to do. Pretty cool. Let's look at 664. F of x is e to the x, so that means that f inverse, making its first appearance, f of x is e to the x, so the inverse function is natural log of x. Let's write an expression for each of the composite functions below and then simplify. This first one's the easiest problem in the world. Any function of its inverse is just going to be x. No problem at all. And the same thing is true at part B. The inverse of the original is also x. So, easy peasy. Now, as far as f and f inverse of 3x goes, look at this, guys. Come on, I mean, you could write it out as this would be e to the natural log of 3x power, but they just undo each other. It's 3x. And do the same thing here. I mean, this is the natural log of e to the 3x. Doesn't matter. The natural log and the e cancel out. You get 3x. Now, if that wasn't enough inverse talk, if you look at the next question, 665, we have a lot of inverse talk going on. Solve each of the following equations for y. Inverses are coming up. They're coming up in our lives. I said that implicit differentiation is one of the big ticket items left. Inverse derivatives is another one. So they're also pretty simple. In this case, I would solve this by taking the sine inverse of both sides for the first one. Sine inverse of x, or arc sine of x. In this case, for question B, we need to undo the cosine inverse. So let's just take the regular cosine of both sides, like that. For question C, solving for y here, well, the first thing we need to do is get that x squared out of the way. So let's take one algebra step and write that sine squared of y equals a 1 minus x squared. The next challenge here is to take the square root of both sides. So we have the sine of y equals the square root of 1 minus x squared. And then finally, we would take the inverse sine. I'm going to barely squeeze it in here. Y is the sine inverse of the square root of 1 minus x squared, like that. Can barely fit it in that little space there. And then, for question, this last question, yikes. Oh, there should be a plus or minus in front of this the more I think about it, sorry. For this last question, sine of y cosine y equals a. Jeez. How can I combine? Oh, jeez. I don't like this question. This question's out of bounds for you guys. It's dumb. You need to recognize that this is the sine of 2x. Or I guess 2y in this case. That's a trig identity that you may or may not have learned last year. I don't know. I guess I got to look at the pre-calc curriculum some more. So now I know that 2y is equal to the sine inverse of a, taking the sine inverse of both sides. And that means that y is equal to the sine inverse of a over 2. I like that problem. And then one more problem for this set. Where are we? 18 minutes? This is pretty good. We got another one of these flag rotating problems, which is the last thing we got to do in AP Calc. Is Chapter 8. We've been setting up for it the whole time. Imagine rotating this flag about its pole and describe the resulting 3D figure and draw a picture on your paper. So this would look like this. I'm going to do this problem off to the side. This is 66. So what we would have is we'd have kind of a diagonal line like this and kind of a cone shape coming in like that. And then the sphere at the end would make it kind of a ball like that. And you'd have your kind of invisible background back there. You're looking for a picture kind of like that. That's what it looks like for part A. As far as the volume goes, it's very easy. The volume is going to be the cone plus half a sphere. We've seen these problems all the time. The cone is 1/3 pi r squared, and the sphere is half of 4/3 pi r cubed. I looked them up. Don't worry, trust me. So you could simplify that 1/2 times 4/3 if you want to, but let's think about what those things are there. For the sphere, the radius is 3. It's 3 in both directions, so r equals 3 in the sphere. For the cone, the radius is 3, and the height is 5. That's nice. They kind of gave us everything, so no real big problems here. We just got to plug it all out. Oh, it's pi r squared h for the cone. Sorry, guys. So for the cone, it's 1/3 pi times 3 squared times 5. You better believe those 3's are going to cancel out. And for the sphere, you're going to have 4/6. I guess we could write that as 2/3. Pi times 3 to the third. And again, you better believe a 3 is going to cancel out. So this is going to end up being, this 3 cancels out with one of these 3s, so it's going to be 15 pi for the cone. And then for the sphere, let's see, this one cancels out, and there's still 2 of those, so it's going to be 9 times 2, 18 pi. So I am getting 33 pi units cubed for that problem. That's what the answer says. I feel good about that. Hey, pretty good. You guys did a great job today, I'm sure. I'm sure you didn't just goof off the entire hour. I'm sure you're feeling pretty beat up by the implicit differentiation. Hey, you keep working at it. You get a little better every day. You guys are doing so well. I'm here to tell you I see the struggle, but it's so productive, and I'm so happy with where it's going. And you guys are awesome. Keep it up. I'll see you in the next video. I'll see you on Wednesday, too. Have a great day.